recording again. I'm continuing recording this class again, similar to the first part. I'm assuming everyone is fine with recording and sharing these slides online on any platform, including Blackboard. All right. So we talked about different type of environments. Now we are looking into the other side of the problem, the agent. So we know now that environments could be observable, partial observable, stochastic, dynamic, static. How about agents? What kind of agents are possible or mostly being introduced and used in this area, in this subject? So first, and probably the simplest one, as I introduced before at the beginning of the lecture, are table-driven agents. If you look at a general aspect, the job of AI is to design an agent program that implements the agent function, the mapping from percepts to action. So this is the basic definition of what we had, like a function which goes from percepts to actions. You give it the percept, it gives you the action, right? We assume this program will run on some sort of computing device with physical sensor and actuator to give us the P, the percept, and also applies the action to the environment. So we call this an architecture. An architecture. So the agent will be, as I said before, architecture plus the program. In general, the architecture makes the percepts from the sensors and available to the program, runs the program, and feeds the program's action through actuators to the environment. So the program we choose must be one that is appropriate for the architecture. So if you are running, let's say, a PLC, you have to have a program suitable for PLC. If you are running a Raspberry Pi, let's say, an embedded system, you have to have a program suitable to that one, and so on. But with all different platforms, you have to have a suitable programming type. So in the table-driven, as shown in the next figure, I'll talk about that. A rather trivial agent program that keeps track of the percept sequence and then uses it to index into a table of actions to decide what to do. So in table-driven, it doesn't mean that it keeps track sequence of percepts and previous actions, right? It might keep it. You might have that I did that, I did that, I did that, now I want to do what? You know, you have sequence of states and actions probably. The table, an example of which is given for the vacuum word in the previous slides, as we had, represents explicitly the agent function that the agent program embodies. To build a rational agent in this way, as designers must construct a table that contains all appropriate actions for every possible percept sequence. The table-driven agent program is invoked for each new percept and returns the action each time. The table must retain complete percept sequence in memory. Okay. The code would be something like that. We call this pseudocodes. Okay, this is a pseudocode for a lookup table or for a table-driven agent. A table-driven agent. So we're assuming that we have perceptions, a sequence initially empty. So we have a memory. We keep those percepts. We have a table, which is a table of actions indexed with percept and sequence. So table, you give the percept, it gives back the action. So percepts to the end of the percepts. So every new percept will be added to your previous percepts. Any new input will be added to the chain of previous inputs I had. Then, based on this, go to the table and find out what kind of action I have to take. So very simple program. I'm assuming that everything is saved somewhere in my program. I have all possible sequences. So a new one comes in, I update my sequence. I check that I did this, and this one. Now the new percept, or I received these different percept, and now I have new one based on this in the table. I'll find out what I have to do. Structure of the agent and environment will be something like this. Your environment feeds the information, or your agent perceives information from environment through sensors. This will go to what word is like now. Actually, the chain or sequence of percepts that you have, that what's going on in my environment, then you take the decision what action I should do. So sensors gives you what environment looks like, and what you should do is happening here. How do you decide based on what you're getting from environment and what table gives you correct answer rules in combination what you have received actually goes and finds what you have to do and sends it back to the environment. So I have a lookup table for entire history. A large, probably, sequence if your environment is complicated. So the P, let P be the set of possible percepts, and let T be the lifetime of the agent, okay? So the percepts I receive and the maximum time or the chain of the actions one after each other that I have for this agent. The total number of percepts my agent might receive. The lookup table will contain, all possible combinations from. You have all different p's to the power of t. So p, number of actions, the set of possible percepts. Set of possible percepts. You might have, I don't know how many sensors. Each sensor might give you how many different inputs. Look at that. And then that gives you how many possible percepts you have. Let's say I have sensor 1, I have sensor 2. Sensor 1 possibilities are like, I don't know, A1, A2, A2, and 2AN. Different kind of results from sensor 1. From sensor 2, I might get B1, B2 to BN. So total possible percepts will be collection of everything. P, number of total possible percepts. So T, or this capital T is the time step. Capital T is how many steps you're gonna continue this. If it's for 1,000 steps, if for millions of steps, if for 10 steps, your collection of the total entries to the table will be sigma, collection of all possibilities of P to the power of T, where T changed from 1 to total number. A simple calculation. Well, I expect you to be able to do that if you have this information. Well, the bad news is if I want to implement that, consider the automated taxi. I'm sure it's impossible for a taxi driving agent to make it a table-based drive, but let's have a look at it. The visual input from a single camera output, at the rate of roughly 27 megabytes per second. 27 megabytes per second for 30 frames per second. And each image is 640 by 480 pixels with 24 bits of color. This gives a lookup table of this size. This is something really, really difficult to handle. So I need a table with the size of 10, with the size of, sorry, 1 with 250 billion zeros in front of it. I don't know how big is that, you know, how much can accommodate. This is nonsense. We can't do that for actually driving agent. And this is a very basic assumption with just a single camera, one single camera. Definitely impossible to do it with this table driven. So how about simpler cases? You know, let's play chess with it, right? Even with chess, if you want to have a table driven chess player agent, total entities will be this number, 1 with 150 zeros in front of it. Huge, huge. It not, and remember, even if it's possible to create that, even if it's possible to save it, okay, for every action, you need a hardware, you need a computer to search within this amount of information to find the right action. Huge. I'm not saying it's impossible. It might be possible, very inefficient, but I don't know. And it's assuming that for each action, there is one single correct move, which is not in many cases. For the case of taxi driver or chess player, you know, there is no single best solution. In some cases might be when you are heading up to a wall, the only solution is you have to stop, you have to press the brake. Or in chess, when you're about to be checkmate, the only best solution is just try to avoid it, right? Or, you know, you can give examples, but mostly in many cases, our agent needs to pick one solution out of several possibilities. Okay, so the daunting size of these tables, number of, and remember, number of atoms in observable universe, total number of atoms in observable universe is 10 to the 80. It's 10 to the 80. It's not just half. It's like 10 to the 70 times less than possibilities of a game of chess. This is total atoms in whole universe, and multiplied by that gives you the total possible moves of possible sequences of move of the chess. So if you want to build up a table for it. And if I assume that I can save every single entity of the table on one atom, which I don't know how is it possible, if it was possible, which is not, we don't have enough even atoms in whole universe to save all this data. So it's not just a matter of having memory, having different things. You cannot save that practically. And as I said, even if it's possible to save it, even if it is possible, at the moment we are on the scale of gigaterabyte, far, far away from those numbers. Even if it was possible, it's impossible to find it in a timely base search inside the table. So it's out of question for many applications. So physical agent can observe that design wouldn't be too time correct, and also even if the environment is simple enough to yield the feasible table size, the designer has no guidance about how to fill the table into this. Okay, and as I said, in some cases, we don't have one single possible output. You have to decide which one is better. Okay. So despite all these, table-driven agent does do what we want. It implements the desired agent function, if we can find it. The key challenge for AI is to find out how to write program that the extent possible produces to the extent possible to produce rational behavior from a smallish program rather than from a advanced table. So the whole idea of the table might be useful if I could write some function to produce those outputs rather than just saving raw data in a table, in a memory. Instead of saving that raw data, if I could write a program to produce that for me, I can solve that. Okay, so we have many examples of this. Right? Think about that. I don't know, for people, you know, all the time probably we didn't happen to me, but I know I had teachers, they were telling us that they had to memorize tables of sine and cosine. They had to memorize some small size table of logarithm, okay? But at the moment, you don't need that. There are calculators, you just enter, there is a function reproducing those values by interpolation or extrapolation of information. So that's a good guiding point, okay? So the question is, can AI do for general intelligent behavior what Newton did for the square root or the square root table? Okie dokie, so it's not gonna work with that. So let's move to another one. The simple reflex agent. This is the simplest kind of agent, and is the well, it's simple reflex. There is a mistake here in typing. I'm sorry. Simple reflex repeated. This one should go. This agent select action on the basis on current percept, ignoring the rest of the percept history. So it says you can simplify your table-driven one if you could ignore sequence of the percepts. Instead of going back to all percepts from the beginning, you just decide based on current percept. You know, what is the input? Reflect based on that, okay? Instead of having percept history. For example, the vacuum agent cleaner function is tabulated previous studies is a simple reflex agent because its decision is based only on the current location and whether the location contains dirt or not. So that makes sense. You know, in some cases, we just need to make decision based on current situation. I don't need to remember what did I do before. Might need for some more advanced learning, smart kind of applications, but for the basic solution, you don't need to, you know, just there is dirt, clean it. There is no dirt, either move or just stay. An agent program for this agent shown in the figure 2.8. Notice that the vacuum agent program is very small indeed compared with the corresponding table. So the pseudocode for a reflex-based would be like this. So what do you have? It just gets the state input and gives the action. Okay. If state is dirty, stop. If location is A, then go right. If location is B, then go left. So it continuously does that. Again, according to what we had before, it might oscillate, might not be the most efficient one, but at least it's a job. At least do the job for us. Structure, something like this. So my environment, percepts from environment, that gives me an understanding on what's going on in the environment, and I need to make a decision. For the decision, it's a criterion action rule. So condition action rule. If then, you see, if condition then action. It's based on if condition then action. Okay, so based on very simple steps of perceive, decide, act. We don't need memory to keep. Well, we do need memory for the program and everything, but we don't need to keep the history of the percepts. So this one might fail if environment is partially observable. If environment is fully observable, we can see everything, it's good. But if it's not, it might be difficult. Compared with a table-driven agent, a simple reflex needs to choose only between its current possible actions. So the total possibility will be that. So it needs a much smaller table, p to the power of t. So in our previous examples, you can just simply calculate that. You see it's much smaller compared with those. So it will be p instead of p to the power t, sorry. So the total possible actions. Simple reflex behavior occur even in more complex environment. Although we understand this is a very simple, very basic sort of agent, but remember, we have that in many even much more complex advanced agents. Even in human, some of our behaviors are basically based on simple reflex. You give the reflection, you know. Just in the taxi driver, if taxi driver sees someone is in front of the car, no calculation, there is nothing, you just stop. All right, just reflex to some input. So you might want to combine this or connect this or relate this with some other type of more advanced agents as well. So it's based on if condition. So more general program, not just for the vacuum cleaner agent. This is again from book, figure 210, simple reflex. It gets percepts and gives action. What do you need to save and have are rules, set of condition action rules. It need to be similar to a table, lookup table again, but this time it's just input, output. So interpret input, percept gives you the state. Based on state and rules, you decide what to do and you make the action for the output. This is the pseudocode for this type of agent. Any questions so far? Everyone is okay? Very good. So the interpret input function generates the reactive description of the current state and rule match, finds the rule match, looking into the table to find what would be the rule based on what we have in the input, and based on that rule finds the matching rule and the correct reflection or reflex for the agent. Okay, simple reflex agent have the admirable property of being simple. That might be good, you know, things small. And you look into nature, many of creatures might have that simple sort of intelligence in, but they turn out to be limited intelligence. The agent will work only if the correct decision can be made, since only the current percept, that is only if environment is fully observable. If environment is not fully observable, it might be difficult to make the decision. In this approach, even a little bit of unobservability can cause serious trouble. For instance, consider a simple reflex vacuum agent that is described from its location sensor and has only a dirt sensor. This is a very good example. So you see in our agent, it has only two locations, location A, location B, and our agent, whatever it is here, and well, it should move to left or right and suck up the dirt. If you assume that there is a problem in observing the environment, for instance, this vacuum cleaner has lost its sense of location. You know, because of the sensor, or because of some environment problem, or it didn't have it at the beginning. Okay, so the problem is it just has two possible percepts, either dirty or clean. So if it's dirty, everything looks okay. It sucks up that dirt and clean. Okay. What should do in response to clean? So if it's clean, it has to move to the other. It has to move to the other square, right? But it doesn't know where it's the square. It doesn't know it should go left or right. Okay, so moving left fails forever if it happens to start in square A. If it has only one choice in the table and it says always move left, so it moves left and there is no left. It's still in A, clean, still in A, clean, still in A, clean. Doesn't move out. All right. Or if it traps in location B, since it doesn't know where it is, and table says next move go to right, it will trap in B. Well, I understand it's super simplified, but for the sake of argument, right? We don't have that. It's possible. Well, this is a very, very simple case, but it's still possible in this sort of the agents. If you have sort of unobservability in your environment, your agent traps in loops of decision. It cannot make right decision because it doesn't have full information, comprehensive understanding of what's going on in the environment. So escaping from these sort of infinite loops is possible if agents again can do some randomized. So you see this randomized thing so many times. So there is something beautiful in random behavior. And well, it's a matter of question if there is something, is there anything really random in this world? What do you think? Is there anything in this world around us, our world, which we know, is there anything really random? Do you know anything which is really random in nature? Is there anything which is really, really random? Do you know anything? Yes or no? Do you have anything which is absolutely random? No one, no thing, not even gut level knowledge can say what is not truly random. No, we don't have any truly random molecules, like Brownian move. So let's say you have I don't know if you know Maxwell Demon. It's a conceptual test. It says that if you have a demon sitting inside an environment and has every detailed information of molecules movement, then it can predict where it goes if you have the information. Because even though Brownian movement is a random movement, vibration inside the atom, if you really, really focus on one single atom, all the forces coming and going, and you can, assuming you can measure, well, I don't know, might not be possible to do that, but well, philosophical question anyway. But in our macro scale world, it's very difficult to find. I'm not saying impossible. I don't know. I never checked every single possibility. Check means thinking, but it's very difficult to find. Okay, but concept of randomization here helps, and that's why later you see in many search-based, optimization-based, actual AI-based solutions, we have a pepper and salt. We have ingredients of randomization in our algorithm. We have a very, very small, acceptable level of randomization to improve the behavior. For example, if the vacuum cleaner perceives clean, it might flip a coin to choose between left and right. In that case, half of the cases it might do wrong, but half of the cases it also might do right decision. So instead of absolute movement to left, absolute movement to right, you can say flip a coin. If it's head, go to right. If it's tail, go to left. Think like that. It is easy to show that the agent will reach to other squares in an average of 2 steps. It becomes on average slower, but it avoids to trap in loops like that. In single agent environment, randomization is usually not rational. In most cases, we can do much better with more sophisticated deterministic agents. Another type of agent, and definitely more advanced, is the model-based reflex. Model-based reflex. So we were happy with the concept of table-driven, but the problem was the full-scale table was impossible to implement. Then we reduced our expectation to just one or very few steps of history of the percepts to make a reflex space. Now from reflex space, we are migrating to another one called model-based. The most effective way to handle partial observability is for the agent to keep track of the world. So try to build up a model of the outside world. That is, the agent should maintain some sort of internal state that depends on the percept history, and thereby reflect at least some unobserved aspects of the current state. You remember I said, would it be possible to create a function to interpolate or extrapolate a sequence of percepts instead of saving raw data? This is one of the solutions. So this internal state is a sort of data representation. It's a sort of modeling outside, which is not in raw data form. So I'm creating, instead of saving, just the number or the sequence or the raw code data, I'm saving information about outside world or sequence of percepts and everything in relation between some internal states. I create a state space inside my agent, and this is a program. This is conceptual. But when I say state space, this is conceptual, and I'm talking. And then I work on the connections and relations. This is a sort of higher level of information saving and more dynamic and probably more effective and closer to nature, similar to things happening in our brain as well. The percept history of the current state. So this knowledge about how the world works, whether implemented in simple Boolean circuit or in complete scientific theory, is called a model of the world. This is the function as Newton-Raphson method we use for square root. Instead of memorizing all square root values for different inputs, all logarithm values for different inputs, we learn how to do the calculation. Here we go. We have that in agent-based as well. An agent that uses such a model is called model-based agent. Updating the internal state information as time goes by requires two kinds of knowledge. To be encoded, I like this. Information is encoded in the agent, okay? Encoded in the agent program. First, we need some information about how the world evolves independently from agent. For example, that an overtaking car generally will be closer behind than it was a moment ago. Second, we need some information about how the agent's own action affect the world. So these are sort of understanding we need to make to create a model from the world. So in the figure 211, we have a simple model-based reflex agent. I'll talk about that, with internal state showing how the current percept is combined with the old internal state to generate the update description of the current state and agent model from Word outside Word. So the program shows in two parts, and the update is shown in figure 212. The interesting part is the function update state, which is responsible for creating the new internal state description. Details of how models and state are represented vary widely depending on type of environment, particular technology used, and agent design. So how do you implement this? Here, as I said, we are talking about concepts. We're getting close to implementation, but still in conceptual level. If you want to make a program to do this, you need to go a few further steps down. So will be modelable like that. Still, I have environment with all those possible structures. Again, sensor comes in. I have two major steps. One major step says what the world is like now, how is outside world right now, and the other one is what should I do? What should I do now? In the previous one, we didn't have anything here. We let that, like, just purely based on we let that to be described based on sensor output. Now in this one, so still I have table of rules instead of table of values. So matching rules and finding what if then decision should be. So this one will be if this is then decision. Instead of that, but on the other side, I'm creating a model of the world. So the input is not just some sensor information to the decision part. Instead of just sensor, our description of the environment through sensor, we also add something because we have state of the environment. We are assuming that, well, I have moved step 1, 2, 3. I have made up some improvements, some faults, some difficulties. Now I know where I am, and how Word evolves according to that. I have learned how Word has been changing. I can track that. For example, in our vacuum cleaner, I've seen that I did A and it was dirty. I did A, it was dirty. I did A, it was dirty. I did A. Something is different. Can everyone hear me?
Now we can.
All right. Okay. So we got into another problem with Blackboard again. Well, so good. We are learning actually. We are building a better model of Blackboard in our brain. All right. So because the previous times, whenever it happened, I just logged, I just closed down and reopened to solve the problem. Now I realize that we don't need that. And also I learned that recording will continue. I don't need to resume recording. All right. Yeah, and in the vacuum cleaner example, as I said, if vacuum cleaner realizes that twice of the time it cleans, it finds dirt in B, it finds dirt in A, it can build up a model. So it can work more efficiently. In a super simple example, see, we have only 2 tiles and just state of dirty, not dirty. And even in that, we can build up a model. can understand a model. Or in taxi driver, after a while, every taxi driver, human taxi driver, builds up a model. They know which road is busier, which one is better, which one right now is under construction. You know, different sort of information both here in this part, in our agent. Pseudocode for this model-based reflex agent will be something like that. You need to have states, agent's current conception of the word state. Transition model means a decision of how the next state depends on the current state and action. So we build up a model. This model might be originally defined or be developed during the work of the agent. Well, different types. Still, we need to learn more to get there. Sensor model description of how the current world state is reflected in the agent's percept. Rules, those tables also, and actions, different kind of actions it takes. So update state based on current state, based on action I'm taking, based on percept we have, based on transition model. How do you transit between states to states? In a taxi driver, well, the road ahead is closed. There is another road on your right. There is another road on your left. And if you turn the wheel, you know that well, you will transit to another state. Now you have new pathway. You have a new and how do you transit from this state to other one? It depends on your action. If you turn right or turn left, take the right road or left road will be a different, and your state will move to another one. Sensor model, and what sort of information I'm getting from sensor and how they're related to environment and so on. You know, for example, in robot, you know that we are getting two-dimensional images, but what we have in reality is a 3D model. So all these will involve. So in terms of running, well, you run one subroutine, sub-function to calculate the next state. It runs another subroutine to find the match for the next for the rule, to see based on rules and state, I'm right in this situation and I have this set of rules, which rule has the best match to my move, and based on that rule, I take an action. That's a pseudo code. It can be transformed to a program if you want to make it a program, but it needs more work. So regardless of the kind of representation used, it is seldom possible for the agent to determine the current state of a partially observable environment. So it's not, it depends. So it's not always possible to do that. Instead, a box labeled what word would is like now in the previous represents the agent the best guess. Sometimes we need to build up stochastic or probability-based model. Most likely it would be like that. With this percentage of chance, it will be like that. With this probability, it will be this state or that state. For example, the automated taxi may not be able to see around a large truck that has stopped in front of it, and can only guess about what may be causing the hold-up. So exactly like what we do, uncertainty about the current state may be unavoidable, but the agent still has to make a decision. Although this can work even in partial information, it is unclear what to do without a clear goal. That's where we get another item coming in, goal-based agents. Goal-based agents are based on a new concept. We define goal for our agent. So far, we have been thinking about what we have to do next based on what I have done before. and I didn't talk about the final goal. You know, in the cleaner, robot vacuum cleaner, we didn't have any specific goal. We had, well, we did have a goal, but it was done through continuous operation. But for instance, in a taxi driver case, you definitely have to have a destination, and everything will be defined based on what is your destination, where is your destination. In many cases, in robotic, in autonomous car, in even even in software AI-based, you might have a goal. You evaluate everything based on how closer they get you to the goal. How easier it would be to get to my goal in this way or another. For example, road junction, the taxi can turn left, turn right, go straight. So correct decision depends on where taxi wants to go. And in other words, as well as the current state description, the agent needs to have some sort of in-goal information that describes the situation that are desired. The agent program can combine this with model, the sum information as was used in model based. So we're trying to build up a model of environment. We also have a goal of our own. We want to find that goal within environment. So it would be something like this. Instead of, well, I would say on top of my decision-making units, parts, if then, or can be table, combination of table, if then. Also, I have to plus add some goal as well. Still trying to build a model of environment, but our decision will be more complicated. Input to the decision maker from this side will be more complicated. Combination of goal with other, short time decision mechanisms. In some cases, goal-based action selection is straightforward. For example, when goal satisfaction result immediately happens. If your goal is short time and happens soon, it will be much easier. But if it's a long sequence, so you need a sequence of of actions per steps to reach to that goal, that would be more difficult. That will be more, it needs more effort. Things like search, I'll talk about that in next chapter. Next discussion will be search. Or planning. You have a set of possibilities. You have to search among those to find the cheapest solution, to find the optimum solution, to find the safest solution, based on how do you define your performance. AI devoted to finding action sequences that achieve the agent's goal. Okay. Notice that the decision making of this kind is fundamentally different from the condition action rules. Okay, described earlier, in that it involves consideration of the future. Okay, what will happen if I do such and such? And will that make me happy? In the reflex agent design, this information are not explicitly represented. So we didn't have those. Would it make me happy, or does this make me look closer to my goal or not? The goal-based agent appears less efficient. It is more flexible because the knowledge that supports this decision is represented explicitly and can be modified. In case of many changes in the environment, the agent can update the knowledge of how effectively its relevant behavior, its relevant behaviors to be altered to suit the new conditions. For the reflex agent, we would have to rewrite many condition rules. So if your environment starts changing, well, all conditions might change. If you have just reflex-based rules, the goal-based agent behavior can easily be changed to go to a different destination simply by specifying a different goal. More general. But the problem is goals alone are not enough. You say, I want to go there, and it wouldn't be enough in many cases. And high quality behavior in the most environment. For example, many action sequences will get the taxi to its destination. Well, from, let's say, from university to airport, you might find thousands, even if you want to do every crazy possibilities, you might go to millions possibility pathways to go there. In the goal-based, all of them might be okay as soon as they get you to the destination. But we also need sort of, evaluation as well. In the goal-based, we have a binary situation. Either we are happy or unhappy. We are satisfied to get to the final goal, or unsatisfied. That's it. Binary, two situations. Either you reach to goal or not. But here we are going to say how happy, how much happy you are. That's you have to have a sort of evaluation on how closer or far, how efficient, or how economy, how is the optimum way of getting to the goal. That's why we define something called utility, coming from economy. If you remember last week, I was talking about utility-based mindset of AI. The quality of being useful, the quality of being good. In two kinds of cases, goals are inadequate, but the utility-based agent can still make rational decision. So in cases when we have conflicting goals, you want to be there, and at the same time you want to pay less. These two are conflicting goals. Paying less means I don't want to consume any fuel, so in the taxi agent I have to stay here. But to get to the goal, you have to consume some fuel, and you pay money. So you can define trade-offs between conflicting goals. Or in some other cases, when you have several goals, you want to achieve all of them. They're not conflicting, but you want to have best of all, okay? And that will help us with this method. We can do that the agent can aim, none of which can be achieved with certainty. We can't do 100% of all of them. We want to have zero fuel consumption, and we also want to get there as soon as possible. All right, so we can define and we can have combination of those. So in partial observability and stochasticity are ubiquitous in real world. So these sort of agents might be very, very useful in that cases. So in utility-based, technically speaking, the rational utility-based agent chooses the action to maximize expected utility based on probabilities you have and the probabilities and the utilities you have. And utility function will be defined, and we try to maximize the expected value of that. So some goals might be this way: global definition of rationality or local rationality. In global means you are considering overall, and in local you are just have a constraint and more limited sort of perception of the system. So in this case, my agent will change as this. So I'm trying to build a model of environment. Also, when I get from sensor, I try to figure out what is this, the environment. And here still, I have to say what I want to do. But before that, I would say, if I do this, what's gonna happen to environment? I try to predict the future before even doing the action. In the previous one, we would do the action and we perceive the consequences. Now we try to predict, if I do that, what's gonna happen next? And how happy will I be with this? If I take this action, how closer I am to my final goal? And based on that, we make the decision. So in that case, we can keep track of the environment and task, and also we need to use some other algorithm to maximize utility for different agents. And this is, well, more flexible, a sort of more complete sort of kind of intelligent agent, but definitely it has higher, it needs, requires higher computational complexity. Means you need better computer, you need better program. It might take longer to do that calculation. And that's where AI needs better computers. That's why you see we need Claude, we need bigger and stronger computations. And the last one we're introducing here are learning agents. In the learning agents, it's based on what we had before, you know, what we have in these sort of agents. Let me jump here. Yeah. We actually extended the previous concept, and this is very close to a new sort of learning, what you see here, learning agents called reinforcement learning method. So I'll talk about that probably in the second half of the course. Here, what I have, I get sensor, and this sensor, and you know, having everything compact in one box, you know, tries to understand that where is my location, how close I'm getting to my goal, and everything else. At the same time, I'm creating an internal critic based on sensor input, based on what I have, based on performance I'm getting from outside. Might not get it. It depends on one. And I will learn. So what did I do and what did happen and how good did I and how bad was the result or good was the result. I start to build a learning element inside my agent. And related to that, also I create a problem to solve. So this is similar to the previous agent, in which that I was saying, well, we were saying that what's gonna happen if I take this action, trying to predict the future. Here is more complex for me. So I have a problem now based on what I have done, what I have received, what will be the solution of that problem? And based on that problem, I can measure and say, all right, my performance gonna improve or I'm gonna lose some performance based on these predicted results. And I will take the action based on that. Well, definitely what you see is a very, very high level, compact description of this sort of learning agents. These learning agents can learn, can adapt themselves based on feedback, based on learning algorithm, and also the exchange of, you know, changes you need to apply and new knowledge I'm learning from my environment and from you know, critique I have and from the policies inside my agent. Okay, but if I be able to implement that somehow, then this has a more complex form, and this is not unique. You for your own agent, you might decide to have some extra blocks or to reduce some blocks or combine some of these basic agent structures together to get more complex, more complete form. The learning agent can be divided into 4 conceptual parts, as I said: learning, performance element, and critique, which are explained there. Okay. The design of the learning element depends very much on the design of the performance. So if you be able to design, my slide is frozen again. That's funny. Now I have to stop that. Not responding. Okay. Yes, it's sorry about that. Well, this is Blackboard problem. I don't think it's your computer or well, no. It's not our problem. Don't worry. And the good thing is it doesn't stop recording, so you won't lose. Okay, can everyone hear me now? And see the slide?
Yes.
Okay, good. Very good. We almost done. Not too many, just a few more slides, and we will be done. Just briefly talking about different components of this learning agent gives processes different parts of a rational agent behavior. Getting information, and this is not a unique definition. Remember that this is just one of the popular, general structure for learning agents. You might decide to have extra blocks or remove some of these blocks or change connection or type of these blocks inside your agent. Okay. And the problem generator is responsible for suggesting actions that will lead to new and informative experiences. Okay, it can be sort of exploring action. When I talk about reinforcement learning in future, well, you will see that an agent might do two sort of activities. One are trying to get closer to the goal, and also some sort of random exploring actions, just to try to just don't miss out anything. It just by following strict rules. Okay, so this explorer here is defined as a problem generator, which is a block to create new sort of knowledge, to bring new sort of knowledge in our agent. The simplest case involves learning directly from the preset sequence. Observation of pairs of successive states of the environment can allow the agent to learn how word evolves. That helps us to learn that and what my action do to the world. All right, so we had all these. Any questions so far? Good. So basically, talking about environment, we learned what sort of environments we have. Talking about agents, we learn basic or fundamental type of agents we can define. But the question is how we implement these agents. How can we make one agent to work? Well, it takes long, actually. It needs more information. It needs programming skill. It needs some other skills because we are talking in high level. We are getting closer, much closer to the core of the problem, but still need other things to learn before we be able to do to create one of these intelligent agents. But to give you a better perspective, to better understanding, just talking about these basic questions, how to write these agents. There are three basic approaches to represent, internal state or the structure inside the agent. One is called atomic, factor, and structures. To understand that, to just clear what sort of approach we might take, look at this structure, and I'll explain what they have. In the atomic approach, the states, internal state of the environment are based on black boxes. I know that I have state A, state B, state C, state D, and transition between the states are defined. But I don't really give any other information about states. I don't need, at the moment I'm at this state and new percept tells me this. And based on rule, I have to decide to go to that state. To go to that state, I have to take this action. Prediction, taking action, and you make the observation. You either are in the target state or not, and you optimize your movement. But the problem, the main consideration is these are kind of black boxes. In the factored form, for state, it's not just a number. You also keep some values inside. You say, okay, I'm at this state. At this state, my fuel is this, my speed is this, my direction is this, my GPS says this, and so on and so forth. You keep some information for state. That makes your program heavier. That makes your states bigger to be described and to be accommodated and to be processed inside your computer program, but gives you a better and deeper knowledge of situation. In some cases, it's not enough just to have states. Say I'm at this state and I need to go to another state. It's better to have some sort of information to make your decision easier, to make other parts of your program more efficient. Okay, and in the third one, in the structured one, each state itself might have a representation of different connections and different information. You are at this state right now, for example, and you came from that state and you need to go to that state. There is a danger ahead. When you are at this state means you have to, fuel up, you have to take care of this, you have to be aware of that, extra information, not just numbers, not black box, not just number, also some relations inside your state. That gives you, more comprehensive information about states and how to transit, but definitely that makes it heavier, bigger, and more difficult to program and to create your agent, the state representation of the agent. I introduce you some keywords and just let you go, because these keywords are everywhere in AI. We might use some of them, we might refer to some of them in future in this class, but all of them are out there. So in atomic representation, as I said, we have a black box representation of the states. Examples and uses of this, related to this type of representation are search algorithm, my next discussion, game playing algorithm, hidden Markov model, a very, very, very HMM, called HMM. Very, very important, approach in AI and in modeling, the hidden Markov model and Markov decision process. Probably the core idea behind reinforcement learning and robotic learning. In most of these reinforcement learning, which are the main approach in robotic learning, and people talking about next generation of learning systems in automotive, in almost everywhere, in reinforcement learning, in RL, Markov decision process are the core item. You have them. We try to model environment using MDPs, Markov decision models. Okay, so they are very useful and very popular in that area. In the factored representation, also you have more information, as I said, and key probably keywords here you need to remember in the second and third one are constraint satisfactions, sort of optimization, machine learning, part of our course, which I'll talk about, proportional logic, planning, Bayesian network, which is part of our, there will be one chapter about that, this, and machine learning, more than one chapter involved with this. Okay. In conclusion, well, before I go to in conclusion, I did talk about this, some other, yeah, and also this, natural language understanding, first order logic, and knowledge-based learning. These are, well, unfortunately, we don't cover all of this in this course. As I said at the beginning, this is an elementary, introduction course to AI. We don't have time to do it, but I will regret if I won't let you know the keywords in probably in your future studies, or where you see or hear about them. You just have something that might ring a bell for you in future, where to go and what to look into it. Okay. So test question, which I do it in class, we don't need that. And also some extra information about weak AI, which I talked about that last week, but I thought it's better to have a slide for it. Weak AI, strong AI, and AI general intelligence, which means in weak AI you have sort of, again disconnected me. All right, so I'm done here. The rest of it will be only the summary and conclusion of the course. I hope you got under ethics. Nothing to explain. That's just a summary. Any question? If you still have me.